Hey everyone, welcome back to my channel. Today we're going to be going through a retirement problem. Just like the previous video, the question is going to be available in the description box below. This question was put together using prior tests and assignments. I just tweaked up the question a little bit, changed the numbers around, added in my own little parts, and tried to make sure everything was covered in case you run into a retirement problem. So we're going to go ahead and read the question here. You're 35 years old and plan to live for 50 more years. To live comfortably, you think you will need to withdraw $8,000 every month during retirement. These monthly withdrawals will be made at the end of each month during retirement. During retirement, you will earn 3.5% compounded semi-annually. You plan to retire at 65 years of age. You would like to set up a scholarship at the university you attended, ABC. The scholarship will be making annual payments at the first payment will occur 5 years after you retire. Payments will be made in perpetuity, which is infinity, and they'll be made yearly. The initial payment made from the scholarship will be $40,000. In order to follow inflation, the payments will increase by 2%, which makes it a growing perpetuity. I'll go over what that means and how to go about that. So the next part, in addition, you want to give back to a foundation of your mother's choice. You want annual payments in perpetuity to start 10 years after your retirement. The annual payments will be for $10,000 and do not grow. So this is not a growing perpetuity, but just a regular perpetuity. You have put $300,000 into a retirement savings account. The account will earn 5% semi-annually. If you need additional funds, you have a savings account set up that earns 6% compounded semi-annually. You will make quarterly payments into the account until retirement. The payments will be made at the end of each period. So the first question asks you, how much money do you require to cover your retirement? So in order to answer this question, you have to think about it this way. How much money will you need from infinity all the way to the initial date of retirement? So you're going to have to find the present value of each cash flow to the date of retirement. So we're going to break it down into three accounts: your monthly withdrawals, your scholarship, and the foundation. We're going to start off with the monthly withdrawal that you want to take out of $8,000. So the input section I have right here is the number of times compounded yearly is 2, the quota rate is 3.5% given by the bank, and the first account we're going to deal with is the monthly withdrawals. So you expect to live for 20 years after your retirement, so you expect to take $8,000 out for 20 years. The number of payments per year will be 12 because they're monthly payments. The total number of payments is just 12 times 20 because 12 payments for 20 years. And the future value will be 0 because you don't need any money after 20 years. The payments will be made at the end of the period. The EAR is found simply by using a formula, which is 1 plus the rate divided by the number of times compounded per year to the power of the number of times compounded per year, and all of that minus 1. And then you can find your EPR by using the other formula, which I have right here. It is 1 plus your EAR to the power of 1 divided by the number of payments per year, and then all of that minus 1. So once you get your EPR, you just use the present value function in Excel. So you're finding how much money you need at the date of retirement to fund just your monthly withdrawals. So the rate is your EPR, the number of periods is 240 payments. The payments will be $8,000 and your future value will be 0 and it'll be ending payments. So you get 1.3 million. Now one thing I just want to point out here is, as you can see, if you multiply the $8,000 by the 240 payments, you get a number of just about 1.9 million, but in fact you only need 1.3 million. Now the reason for this is because while the $1.3 million is sitting in the bank, it's accumulating interest. So you only need 1.3 million, but in fact you're going to be taking out 1.9 million, and that's thanks to the interest rate. Just something I thought you'd want to know. So the next question is going to be the next step in finding out how much money you need is dealing with a scholarship. Now the trick with the scholarship is it's a growing perpetuity, which means the payments will go on forever, infinity. Or at least in a perfect world. So the payment amount is set up at $40,000, which is your initial payment. The quota rate is still 3.5%. The number of payments per year is 1. The payments are made at the end of the year. The number of times compounded per year is 2, semi-annually. The growth rate is 2%. And I have this little row here 1 year before first payment is 4 years after your initial retirement. And I'll explain this using a timeline here. So as you can see, the first payment occurs 5 years after the retirement starts. So the thing with the perpetuity formula is it finds the present value 1 year prior to the first payment. So I pulled up the equation over here. It's the $40,000 will go right here, divided by the EAR that we found minus the 2% growth rate, and that gives you the present value, which is 1 year prior to the initial payment. So you can see right here the timeline, the present value of the perpetuity is at year 4. So once you find that present value, you have to discount it back again 4 years to the initial date of retirement. And I'm going to show you how you do that over here. So you have your first year before the first payment is made. Sorry, 1 year before the first payment is made is year 4. You found your EAR using the same formula. So your present value is the equation that I just showed you. It's $40,000 divided by your EAR minus your growth rate. And that gives you the present value at year 4 of the perpetuity. Now that's not enough because you have to discount it back now to year 0 of the retirement, because that's how much money you need for, at the beginning of your retirement. So in order to do that, you can use the present value function built in Excel. The rate is your EAR. The number of periods is 4 because you have 4 years until the perpetuity starts. And your payment amount is 0 because there's no payments being made for the first 4 years. The future value is going to be your present value of the perpetuity at year 4. And your type is 0 because the payments are made at the end. And that's how you find the amount that you'll need for your scholarship. Now finally, the foundation. The foundation is basically a perpetuity, just there's no growth to it. So it's set up exactly the same as a scholarship. You have your $10,000 payment. The number of payments per year is 1 because it's annually. The payments are made at the end of the year. The growth rate is 0. There's no growth rate. And just like I did before over here, 1 year before the first payment is year 9. So at year 10, you make the first payment. But the present value of the perpetuity is at year 9. And then you discount from year 9 all the way to year 0 of the retirement. So just like the last time, we're going to use that formula, except we don't have a growth rate now. So it's simply $10,000 divided by the EAR that you found, and that gives you $283,000. And then we have to discount it back again 9 years. So the rate's the EAR. You have your 9 years of discounting to do. No payments for 9 years. Your future value is the present value of the perpetuity at year 9. And your type is 0 because they're end of year payments. Actually, there's no end of year payments, but we just leave it at 0. So you have to add up all those requirements in order to figure out how much money you need at the date of your retirement. So you add up the present value of the foundation, the present value of the scholarship, and the present value of the monthly withdrawals, and you get $3.8 million. Step 2, how much money will be available in your retirement account when you retire? Shouldn't be there. So what you do here is you know that you only have one account, your retirement savings account, where all your money is going to be coming from. It looks like that's not going to be enough, but we'll just go through the question here anyway. So the number of times compounded yearly, so this is our input section. The number of times compounded yearly is 2. The quota rate is 5%. The number of years is 25 years because we have 25 years until we retire. The payments are going to be made at the end. That's not relevant to this though. Your EAR is found using this equation. I'm not going to go through the equation, you already know how to do that. And the present value is $300,000 because that's how much money we're putting in the account today. And you're gonna find out how much money you'll have in 25 years. So you're gonna use the future value equation. Your rate is going to be your EAR. Your years is 25 years. Sorry about that, guys. So continuing on to what I was saying earlier, your years is going to be 25 years. The payments are 0. There's no payments being made. You're just putting that $300,000 into the bank and you're letting it sit and build some interest for you and make some money. Your present value is negative $300,000. The way I like to think of it is there's a negative sign there because you're giving $300,000 to the bank, so it's leaving, therefore it's negative. And the type is 0. That's irrelevant to this. and you get 1 million, just over $1 million. So now we can see that there's a deficit here because we're gonna have $1 million, but we need just about 3.8 million. So we're 2.8 million short. And we know from the question that if we are short, we have an additional fund of a savings account set up that earns 6% compounded semi-annual interest. You'll make quarterly payments into the account until retirement. The payments will be made at the end of each period. So we're going to have an input section for our savings account. The number of times compounded yearly is 2 because it's semi-annually. The quarter rate is 6% given to us. The years is 25 years. We have 25 years to make up for that shortfall. The future value is the shortfall. The payments are going to be made at the end of the quarter. The number of payments per year is 4 because it's quarterly. The total number of payments is 100 because we have 25 years and we have 4 payments per year. The EAR is found using the equation from before. Same thing with the EPR. And then we're going to use the payment function to figure out how much money we need to put into the account each quarter to make up for our deficit. So we get 12,466. The rate is the EPR. Again, number of periods is 100. The present value is 0 because you have no money in the bank currently. The future value is your shortfall, and the type is 0 because they're made at the end of the quarter. So once you get all that, you can move on to D. You are prepared to increase the quarterly payments by 1% each month. What will be the amount of your first monthly payment? Now, these questions tend to be a little bit tricky, and everyone has a different way of doing it. The way I like to do it is I like to treat each payment as a separate cash flow and basically discount it forward. So see how much each cash flow will be worth up until the date of retirement. So it'll be 25 years forward. So I'll show you what I mean. So this is our input section here. The total number of payments will be $100 because they're quarterly payments for 25 years. The quarter rate is 6%. This is all the same as the savings account setup, the input section here. That's all the same. The growth rate is 1%, so each payment will increase by 1%. Our EPR is the same, and this is kind of the table you have to create. So what you're going to do is you're going to set your first payment. You're going to put in a random value, doesn't matter what it is, and your future value is going to be future value. The rate is going to be your EPR. So for the number of periods, basically what you're doing is you're trying to see how much this $8,000 will be worth in 99 periods forward. So what you'll do is you'll go 100 minus the payment number. Your payment will be nothing because you're treating each present value as a cash flow. Your present value will be negative. This is just to account for the negative sign. Oops. Negative, and your type will be 0. Once you have all that done, make sure that your rate is an absolute reference. That's fine. And your present value, that's fine. So you press enter. So basically this $8,000, the first payment in 99 payments will be worth $34,000, just this one payment. And we have to make sure that all of this accounts for the shortfall that we're going to have. Because clearly we can see that there's going to be a $2.8 million shortfall. So we have to make sure that we can account for it. So payment number 2 will be an increase of 1%. So remember that each payment increases by 1%. So it's going to be the previous cell times 1.01. So we can see that it increased by 1% here. And then if we did everything right, we should be able to drag the cell down. And yep, everything worked out. Okay, so I think if we keep dragging this down, it should continue to add everything. Yeah. So it looks like I'm running out of time on this video. I'm just gonna end this video here, and I'm gonna continue off on a second part on the next video. So I'll see you there.